My talk focuses on measuring and modeling variability of solar Balmer lines. However, I would like you to take it mostly as an example of our capability of modeling the variability of solar lines and the difficulties that we're now facing. So I think it's very well known to everybody that the cores of the upper Balmer lines form in the chromosphere. So one would expect that the variability of indices derived from Balmer lines to follow the variability of other chromospheric indices, as for instance, the calcium index. However, we know that this is not the case. We know that this is not the case, for instance, for stars, for which in particular the H-alpha index, because the correlation between the H-alpha index and the calcium 2 index varies in a complex way with a lot of activity and with the metallicity of a star. This is true also for the sun. The plot on the left here shows, for instance, the correlation coefficients between the calcium and H-alpha index investigated by Meni and Delfos, who looked at about 30 years of solar observations. And as you can see, the correlation coefficient between the two indices varies with time and reaches a minimum during the periods of lower activity. The authors interpreted these results as due to the fact that during period of lower activity, the relative contribution of filaments is higher. However, overall, the two indices are positively correlated. This result has been recently challenged by Maldonado and collaborators, who analyzed about 3 years of solar observations with HARPS, and they found that H-alpha, H-beta, and H-gamma are anti-correlated with the calcium 2 index. So to investigate these differences and to understand them, to understand their origins, we decided to look at different types of data sets and to compare them with models. The first difficulty that we found is that if you look at publicly available databases, we find that actually there are not that many measurements available that allow to study variability of solar lines over long temporal scales at high spectral resolution. So we decided to look at radiometric measurements. In particular, we analyzed OMI and TROPOMI measurements to look at the variability of H, beta, gamma, and delta, and SCIAMACHY and GOM2 to look at the variability of the H-alpha. The problem that we found with these instruments is that they are affected by long-term trends, which are instrumental, and which we had to remove. And so this means that we couldn't use this data only to look at the variability on the solar radiation. To look at the variability on longer timescales, we utilized ISS data. However, this instrument allows us only to look at the variability of the H-alpha. We then used other observations, which allowed us to look at the variability of other indices. In particular, we looked at the total solar irradiance, the calcium 2 index, the dark photometric index, which is basically strongly correlated with the variation of the area of sunspots, and other chromospheric indices as the magnesium 2. So for the model, we used a semi-empirical approach. Basically, we utilized full disk observations acquired with a precision solar photometrics telescope between 2005 and 2015 to single out different types of quiet and active structures. We then utilized a radiative transfer code, in particular RH, to synthesize non-anterior the Balmer lines. We use for these models, for the synthesis, two sets of atmosphere models. The first one published by Fontella and collaborators in 1999. The second, the sets of models published by Fontella and collaborators in 2011. The plot in this slide compares the fluxes obtained from the quiet sun from the two sets of models and how they compare with the reference FTS spectrum. And as you can see, the quiet sun from the sets of 2011 models seems to slightly better reproduce the observations. Then once we have, then we reconstructed the variability on lines by combining the synthetic spectra with the area coverage of feeders derived from full disk observations. So why did we decide to analyze two sets, synthesis obtained from two sets of atmosphere models? So the reason is that the 99 models are those that are most widely used for solar irradiance reconstructions. However, as I showed you before, the 2011 models, the quiet sun seems to best reproduce the reference spectrum. Also, recently, An analysis carried out on high spatial resolution observations of H alpha shows that the 2011 models very well reproduce certain properties of these lines. So this slide summarizes our results based on the solar rotation time scale. The plot in particular shows the Balmer index derived from the OMI observations, and the other color lines depict the variation of other indices rescaled to fit the figure. As you can see, the magnesium for the first three rotation, the magnesium index seems to produce a variability that the peak more or less have the same height. If you look at the Balmer index, this is not true because the three indices seem to decrease. And this trend more closely follows the variation of inverted TSI, and in particular more closely follows the variations that we find for the dark index, which again is very strongly correlated to the variation of the area of sunspots. I'm showing here your results obtained on short temporal range, but similar results were obtained when looking at the whole data set that we have available. And we came to the conclusion that these trends suggest that the variability of Balmer lines on the rotational scales mostly induced by sunspots, and that the contribution of Fagoler network is much lower. And this is confirmed also by the model, which here in this plot are indicated with the green and red lines. So in this respect, Balmer lines seems to behave more as photometric indices rather than chromospheric ones. On the longer temporal scales, we found that both models and observations produce an H alpha index that seems to be correlated with the activity. However, quantitative analysis between the observation and the models is hampered by the fact that we think that ISS observations are affected by some long-term trends, which are still under investigation. The plot on the right shows the correlation coefficients between the H alpha and calcium. And as you can see, in agreement with the results presented by Meunier and Foss, we also find that during periods of lower activity, the correlation coefficient between H alpha and calcium 2 seems to decrease. And the agreement here is qualitative between the models and the observations. Qualitatively is pretty good. However, I would like to point, thank you, to point your attention on the fact that in our model, we do not include the effects of filaments. The lower correlation coefficients found during periods of lower activity instead due to the fact that the models indicate that the H alpha is less sensitive to the presence of network, whereas the calcium is much more sensitive to the presence of these type of structures. Now, can we use these observations to distinguish which sets of models best reproduces the properties of the sun? To answer these questions, we looked at different metrics to evaluate the differences between the models and the observations. And in particular, I looked at the mean absolute percentage error and the Pearson correlation coefficients, which are reported in this table. Overall, we found that the FAL 99 model seems to better reproduce observations over the FAL 2011 models. So I hope that my presentation convinced you that it's very important to compare models with observations, because they allow us to explore the different physical phenomena that drive the irradiance variability. And in this case, this analysis has allowed us to rule out that filaments may play a major role in driving the variability of Balmer lines. However, there are some issues here. The first one is that on the rotational scale, the agreement between measurements and observations seems to be pretty good. However, there are still some differences. And are these type of differences and uncertainties acceptable for transmission spectroscopy? And I think this is probably a point that we should discuss in this group. Also, the other problem that we have, and that the quantitative analysis on longer temporal scales is hampered by the quality of data. Again, it's very difficult to obtain this type of data. We really need data that are stable over long-term temporal scales. And I think it's very important that we push our supporting financing agencies to promote and to support these type of measurements. And the second problem that we have is that I've shown you that the FAL 99 model seems to best reproduce the observations, the variability of Balmer lines. However, this seems to be in contrast to results that we obtain when we look at other observables. And this, of course, from a theoretical point of view, is unacceptable. And it also points to the fact that it's very important to validate our models with independent sets of observations. But even here we have a big problem, which is that the lack of available measurements for this type of validation is almost embarrassing. And the reason is that in the last 40 years, most of solar observations have focused in analyzing very small spectral ranges, which are not ideal for this type of validation. So I thank you for your attention, and I'll accept questions.
Thank you. So we have a time for a very quick question. I don't see anything in Slido, but I was wondering, now that you were advocating for more observations, what observations would you really need? What would be your wish list?
What I had in mind is high spatial resolution observations. And I mean, here, something of the order of sub-arc second, 1 arc second, sub-arc second spatial resolution, performed in high, wide ranges of spectral ranges. This is what we would really need. And something in moving. I mean, it's not that the type of available data is 0, but definitely really starting. And I don't think we have the right type of instruments yet.
Okay, thank you. I can now see a question in Slido for you, but I mean, I think we have to move to the next talk, but you can have a look at it in Slido.